So hello guys, my name is Afdal. So me and my group and I will present about the computer architecture about pipelining and SMP, which is symmetric multi-processing. So I'm going to continue this. So did you ever know that modern computers can handle many tasks efficiently thanks to a technique called pipelining? It works by breaking tasks into smaller steps that can be processed simultaneously, making things faster and more efficient. This simple technique is very but brilliant method helps us perform more in the less time. In this presentation, we discuss how pipelining works, why it's powerful, and the challenges it faces. So by the end, you understand how it keeps your device running smoothly every day. So I'm going to pass to Nadia for her to present about the design of computer architecture design.
Thank you so much, Afdal. I'm Nadia and I'm going to be explaining about our system architecture design, the pipeline processor. So as you can see in our design, we have the control unit and then the processor with the register and also all the 5 stages. So there's also the input as well as the output. So the pipelining undergoes 5 stages, namely instruction fetch, instruction decode, instruction execute, memory access, and write back. So now I'll be explaining about each stage. So the first stage is instruction fetch. So the processor will retrieve any instruction from the memory and then stores it in the first register, which is R1. So in the second stage is instruction decode. So this is where the fetch instruction will be decoded and then it will be broken down into simpler components so that it can be executed in the next stage. So the next stage is the third stage is instruction execute. So the processor will perform the operation specified by the decoded instruction, meaning that they will execute whatever instruction it is. So now for the fourth stage, which is memory access. Memory access is only required if the instruction requires data from the memory. So in this stage, it will fetch the necessary data and then stores it in register form. And then the fifth stage, which is the last stage, is the write back. So the write back is the results of the execution that are written back to the register. So the updated register will reflect the output, which is then displayed. So later, once you're done with stage 5, it will be output. So next, I will be explaining about symmetric multiprocessing SMP. So this is our design for our SMP, where you have the main memory I/O devices connected to the bus system and then connected to the L2 cache for each processor and then L1 cache for each processor. This is processor 1, processor 2 and processor N, meaning there can be multiple processors. So SMP is symmetric multiprocessing. It is a system where multiple processors will share the main memory and as well as input and output devices. So all of these processors will communicate with the shared memory via the system bus. So the system bus allows it to read and write from the main memory and also to the main memory. Okay, so in SMP there's also data coherence, which ensures consistency between main memory and caches. So data coherence means the data will be the same for each processor. So if they update a certain data from processor 1, processor 2 will also receive the same updates. So it can be maintained using write back and write through. So in write back, any changes in the data will go to the cache first and then the memory. But for write through, any changes in the data will go to both cache and memory simultaneously. So for example, to make it clearer, this is how it would basically maintain the data coherence. So for example, in processor 1, the processor 1 will read the data from the memory and then after reading the data, it will be updated on its cache. So later, processor 2 will take the same data, it will read the same data, but then it will modify the data in its cache. So the modified data, for example, they will edit something. So now processor 2 has the updated data. So later, processor 1 will detect that updated data and then it will fetch the updated data from either memory or processor 2's cache. So this is how you maintain data coherence inside of an SMP. That's all for my part, so I'll be passing it on to Ray.
Hi, my name is Ridwan and I'm going to show you the performance analysis for a pipeline and SMP systems. So first off, for pipelining, Assuming that each instruction requires a base clock cycle of 10 units in a non-pipeline system, and that a pipeline has 5 stages, given n is equal to the number of instructions, so in this case, let's say we have 20 instructions, n is equal to 20. In a non-pipeline system, it would be n times the base clock cycle, which is 10. So it will be 20 times 10, which gives us 200. So for a pipeline system, it's a bit more complicated. So you have 10, the base clock cycle, plus with n minus 1. It's n minus 1 because in ideal conditions, the first instruction requires 10 units, while subsequent instructions, so every instruction after the first one only requires 2 units to be completed. So it's n minus 1 because we're taking out the first one times 2. In this case, it will be 10 plus 20 minus 1 times 2, which nets us 58. To calculate the speed up, it's very simple. You just take the non-pipeline value and divide it by the pipeline value. So it will be 200 divided by 58, which nets us 3.45. Moving on, we have the performance analysis for the symmetric multiprocessing, or SMP for short. Given that we have 100 tasks in our workload and that each task takes about 5 units of time, assuming ideal load balancing in a single processor system, not using SMP at all, will be the workload times with the units per task or time per task. So in this case, it will be 100 times 5, which gives us 500 units. In a system that implements SMP, or in this case a 2-processor system, it will be the workload divided by the number of processes in the system times with the time taken per task. So it will be 100 divided by 2 times 5. 100 divided by 2, it's this, your 50-50 halving everything, so it will be 250 units at the end. To calculate the speed up, again, it's just the first value divided by the second value. So 500 divided by 250, that's us 2. To calculate the throughput, for a 1-processor system, it will be the workload divided by the first value, which gives us 0.2 tasks per unit. And for a multiprocessor system, it will be 100 divided by 250, which gives us 0.4 tasks per unit. Now I'll pass it off to Belron for the critical analysis. Thank you.
Thank you, Red. So, hi, my name is Varun. So, I'm going to be talking about the critical analysis for pipelining. So, I'm going to be explaining about the 3 things here, which is the type of hazard, the potential hazard, and the solution for the hazards. Okay, so the first one I'm going to get into is the structural hazard. So, the issue arises when the instructions compete for the same hardware resources. So, in order to mitigate or solve the hazard is we can use a hardware duplication to provide separate memories for the instructions, and we can also utilize scheduling, which can help the instructions to schedule, when to come in, when to go out, something like that. So next one is data hazard. So data hazards happen when an instruction depends on a result which hasn't even released yet, which can cause the performance to drop and things to go slow. So in order to solve it, we can implement data bypassing. So when the result hasn't come in yet, another instruction can go in first to another thing. So the next one is also we can do in the instruction reordering, which is like what I said just now. If an instruction hasn't come in yet, it can jump to another thing first. Like it can jump to something else before going to this. So by solving this, we can speed up the instructions and solve the performance drop. So for the third one is the control hazard. So this issue happens when the pipeline makes an incorrect prediction about the instructions now. So in order to solve it, we can use pipeline flushing. So when this system gets the wrong instruction, it can flush its system so everything resets. So it doesn't slow down when something happens, when it jams, when it delays. So next one is also we can install branch delay slots. So when someone sees there's something wrong, we can insert a delay slot which makes the instruction go in slower, so other instructions can go in first. So that's all from me. I'm going to pass the next part to Ayin.
Thanks. Okay, so hi, I'm Ayin, and I'm going to be talking about the hazards for SMP and the solutions for it. Okay, So first up, we have memory contention. So what's memory contention? Okay, so it happens when all processors share the same memory and try to access it simultaneously. Okay, so what does that do? It'll slow the entire system. So what can we do about it? Okay, so we can optimize the software and data layout. By doing that, it can minimize the remote memory access. What else can we do? We can adopt the non-uniform memory access. Okay, so that allows the division of memory into local memory. Next, I'll be talking about the scalability issues. So when the number of processors increase, the traffic and memory contention grow. Okay, so what can we do to counteract that? Okay, so we can optimize the software to reduce the shared memory usage, and we can once again adopt NUMA. Okay, so that properly divides the memory regions and reduce traffic. Okay, so for final part, we're going to be talking about load balancing. Okay, so an uneven task distribution can lead to one processor being overloaded while the other is idle. So to avoid that, we can implement dynamic scheduling tasks to processors based on their availability. And we can also implement work stealing for idle processors to steal tasks from busy processors. That's all for my part. I'm going to be passing on this last part to Akmal.
And now I would like to present about conclusion. So through this assignment, we learned about parallel processing by designing a system that combines pipelining and symmetric multiprocessing SMP. Pipelining boosts performance by processing multiple instructions simultaneously, while SMP distributes tasks across processes and uses shared memory to handle complex workload more efficiently. We face challenges like calculating pipelining efficiency, analyzing SMP, and designing a basic parallel processing system. However, we managed to overcome them by finding effective solutions. This experience highlighted how architectural decisions impact system performance and the importance of strong theoretical designs. Pipelining improves CPU performance by running multiple instructions together, reducing processing time, while SMP enhances performance by adding processes. Together, these techniques show the value of parallel processing in modern computing systems. Thank you.